Hello everyone, welcome to this virtual tour of ESO's Paranal Observatory. My name is Hector and together with Felipe we will be your guides today. So I'll introduce myself first. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany, and I've been a member of the team of guides from Paranal Observatory since 2019 when I was doing my master's in Antofagasta. I'm currently working on topics related to galaxies and the circumgalactic medium, that is the environment that surrounds galaxies. And as I mentioned today, I'm joined by Felipe. Felipe, how are you?
Hi everyone, hi Hector, hi the people see us in the new tour, virtual tour. I'm Felipe Zurita. I'm an astronomer with a degree in astronomy in University of La Serena. I've been working from ESO in guiding in La Silla about for the past 9 years. It's old. I'm old. Today I will the producer to show you the telescopes and all things you in this particular Paranal Observatory. So I hope you enjoy. Remember, leave your comments, greetings, question about astronomy, telescope, whatever you see in the virtual tour. So come on, Hector, let's get started.
Okay, so Felipe mentioned you can leave all your comments, greetings, and questions in the chat, and we'll have some time to answer them. So let's start with our tour today. So the first thing we have to do is tell you about ESO. So ESO is an international organization that is comprised of 16 countries that you can see there on the screen. So we have Denmark, the Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, Czech Republic, Austria, Switzerland, Italy, and we also have two non-European countries there, Australia and Chile. Australia joined very recently as a strategic partner of ESO, and Chile is the host country. The telescope that ESO controls are in Chile. So I should also mention that ESO is the European Southern Observatory. That is the name of the organization. It started in the 60s, and the first place that they have in Chile was La Silla. And in the next image, we'll see some of the different places that we have with different observatories. So there you have. So as I mentioned, La Silla was the first one. In the 1960s, ESO was finding places to build new observatories, particularly in the southern hemisphere, and Chile was trying to attract human capital to the country. So they come to an agreement, and La Silla Observatory was built in the 60s. So in La Silla, we have the entity, the New Technology Telescope, and the ESO 3.6-meter telescope that has an instrument called HARPS that is specialized in the detection of exoplanets. Further north, in the Changnan-Tor Plateau, we have two sites there. We have ALMA and APEX. So APEX is a single antenna, and in a way, it's a bit of a precursor of the technologies that were later used in ALMA. And in the case of ALMA, it's not just ESO that controls ALMA, but it's a consortium between ESO, United States, and some countries in Asia Pacific. And in the same region, the Antofagasta region, near to the coast, we have two places there. We have Paranal and Armazones. So Paranal is the place that we're going to visit today, and the star instrument there is the BLT, the Very Large Telescope. And we also have the interferometry mode of BLT, the BLTI. In addition to that, we have two survey telescope, BST and VISTA. And very near Paranal Mountain, there is Armazones Mountain, and that is the place where the ELT, the Extremely Large Telescope, is currently being built. And in between the Paranal Mountain and Armazones Mountain, uh, there is a place where CTA South is going to be built, and this is going to be an array of telescope that is going to be specialized in the detection of gamma rays. So this gives you an idea of the different places that ESO have in Chile and the different observatories that we have. So let's travel now to our destination today, Paranal Observatory. So we're virtually traveling above the Atacama Desert. We're 1,600 kilometers north of Santiago de Chile, the capital, and we're at about 130 kilometers of Antofagasta, the regional capital. The nearest city is Taltal, that is at about 90 kilometers. We can see there in the background Paranal Mountain, and Paranal Mountain is part of what is called the Cordillera de la Costa, the Coast Mountain Range. This is a coastal range that extends in Chile, very near to the coast. We are just 12 kilometers in a straight line to the coast. So you might be wondering, can we see the Pacific Ocean in this image? And we could, except that it's covered by clouds. We can see some haziness there in the background. Those are clouds, and below those clouds is the Pacific Ocean. So you might be wondering, why so many clouds in the desert? Well, this is a consequence of the Humboldt current. This is a mass of cold water that comes all the way from the Antarctic and goes through the coast of Chile and Peru, and it produces an effect that is known as thermal inversion. And this basically makes that all the humidity and all the clouds they form at about 1,000 meters at above sea level. And here, the coastal mountain range has mountains that are about 2,000 meters above the sea level, and Paranal Mountain is 2,600 meters in height. So here we are above the clouds. And to the other side, to the east, we have the Andes. And the Andes have very tall mountains that are about over 6,000 meters high at this location. And they stop the cold air and bad air that is coming from Argentina and also Bolivia. And the result of these not two natural barriers is the extremely dry desert that we have here. The Atacama Desert is one of the driest deserts in the world. So now let's take a closer look to the mountain. And here we can see that the top of the mountain was cut, a bill was wrote, and we have the different telescopes with their names. I also would like to mention that Paranal in the Quechua language means whirlwind, and this could be a reference to the whirlwind that sometimes forms in the desert due to wind. But usually the weather here is very calm. We have an average of over 300 clear nights per year when we can observe the whole night. So it's one of the most the better places in the earth to do astronomy. You can only get better conditions than this if you go to a space telescope. So with this, now let's go to the summit of Paranal Observatory. So here we're in the main platform of the observatory. And let's start by just taking a look around. So here we're looking to the west. We can see all these clouds here in the distance. Below those clouds we have the Pacific Ocean. Then we continue. Now we're looking towards the south. You can see this beautiful desert landscape that we have in this part of Chile. And over here we can see the Armazones mountain that is very close to Paranal. And it's actually the observatory, the telescope is going to be controlled from here because we already have a control room here. And over here we can also see there's a little arrow here. This is a volcano, volcano Yuyayaco. And this is actually the frontier with Argentina. And Chile is a very long but very narrow country. And we're actually in one of the widest part of this country here. But from here we can see the frontier on one side with Argentina and to the other side with the Pacific Ocean. Now, here we have the telescopes of Paranal Mountain. And the first thing that might caught your eye is that the PLT is really not a single large telescope, but it's four telescopes we have here. So we have here UT1, UT2, UT3, and UT4, where UT stands for Unit Telescope. So in addition to this UT, and they are very big, they have a primary mirror that is 8.2 meters in diameter. We also have some smaller ones. So we have one here, another one over here, and two more over here. These are the auxiliary telescope or AT. Their primary mirror is 1.8 meters. And as you can see, they are on top of tracks. That means we can move them. And we have these octagonal trapdoors. There are about 30 of those in the platform. We can put the ITs in any of those 30 positions. Now, why do we need to do that? Or what is the usefulness of that? Well, the ATs, they work doing what we call interferometry. The ATs, they can also work in interferometry, or they can work separately. And we have a small video that helps us explain this a bit. So when we're doing interferometry, we are observing the same object with two or more telescopes at the same time. And what we do here in Paranal is that we collect the light and we send it through underground tunnels to the central building, that is the interferometry building. The light is combined completely analog. This is not a post-processing thing done with computers after the image were taken. This is done when we're taking the images by sending the lights using mirrors and underground tunnels to the interferometry building. Now, when you do interferometry, the distance between the telescope is important. This is what we call the baseline. And the baseline is going to determine the resolution that we're able to achieve. So when we're using the four big ones and also the four small ones, the baseline is at about 200 meters. And this means that roughly we get a resolution equivalent of a single telescope of 200 meters in diameter. But what is this resolution thing I'm talking about? So this is about our capability of separate two objects in the sky. If two stars are too close together, using just one of the UTs, we might see them just as a single star. But if we do interferometry and we improve the resolution, we can see them as two separate objects. So to give an example of this, using interferometry, if we were to put a car on the moon, we would be able to differentiate the lights coming from the two different headlights. So that's the level of resolution we can get with this. So let's go back to the main platform. Okay, so the UTs, they also have names in the Mapudungun language. So astronomers, they are not very good at naming things, hence the names UT and AT. But there was a contest at some point to give them a better name. And it was chosen the names in Mapudungun. And for UT1 is Antu, which means the sun. For UT2, Queyen, which means the moon. Then for UT3, Melipal, which means something like 4 stars, and it's a reference to the Southern Cross constellation. And then we have Jepun, which means something like the star of the evening, and it's a reference to the planet Venus. So Mapudungun is the language of the Mapuche, the natives of the central and southern parts of Chile and also Argentina. So we have those names. Now, the four big telescope, they have the same structure, but they have different instruments. Each one of them has spots for three different instruments, completely different, and the four they have different instrument in itself. But the structure is the same. For matters of time, we cannot enter the four of them. We're only going to enter just one of them. But as I mentioned, they are pretty much alike. So we're going to go into UT3 or Melipal. So here we are inside the telescope. We are in what would be the fourth floor of the telescope. And this is very big. If we take a look around, we can see some engineers and technicians working during the day, and this gives us an idea of the scale of this telescope. This is very, very big. Now, the primary mirror over here is a monolithic mirror made out of a single piece. There are bigger telescopes, but they now use segmented mirrors. These are the largest mirrors that have ever been built. Now, the mirror is made out of a special material called zero dur, and this is a mix of glass and ceramic. The mirror plus the white supporting structure weighs at about 22 tons, and despite being 8.2 meters in diameter, is only 17 centimeters thick. Now, what gives it the reflection of the mirror is a very, very thin layer of aluminum, and this is thinner than a human hair. I'm talking about nanometers here. So here's the primary mirror. On top, we have the secondary mirror, and there is a third mirror that is at the center here. We cannot really see it well in this image. Now, how does this work at night? Well, first we must open the enclosure. And we have here, if we follow here, there is an L-shaped window that opens to the sides. We open that and we can look into the sky. And to point to a different object, a different galaxy or a different star, we have to move the telescope. This telescope has two motions. So the first one, this blue supporting structure will be the mount of the telescope that is fixed. And this white part, it can be tilted. That's one motion. For the second one, we can see that this part of the floor is separated from the rest. That is because this part can rotate 360 degrees. So combining this rotation with the inclination, we can point at any place in the sky. Now, we have a small video to show the path of the lights when we are using the telescope. And this is obviously exaggerated. The enclosure doesn't open that much. So the light is going to come from the sky, going to hit the primary mirror, that is a concave mirror. Then it's going to bounce and go to the secondary mirror, that is a convex mirror. And it's going to bounce again to the tertiary mirror. And the third mirror can either send it to the right, or we can rotate it so it's sent it to the left, or we can just let the light go straight through. That way we can select which instrument we're going to use. As I mentioned, we have spaces for 3 different instruments. And we can only use one of them at a time. So now, let's go back to the telescope. And we can see here the one of the instruments, in this case BIMOS. And if we go below, we can see the one underneath the telescope that we have over here. In this case, it's called Symphony. Now, one of the reasons why Paranal Observatory is one of the most advanced in the world is because of the active optics. So you see these gray boxes over here? These gray boxes are the so-called actuators. And they are like pistons. They can push and they can pull. So why are they here? Well, if the mirror were to be made out of glass, like the mirror in your house, when you point the telescope at a star, if the inclination of the mirror could be so big that the weight of the glass is in itself would cause it to break. The stress would be too high. So the solution was to use this special material called Zero that has a bit of flexibility, so the mirror doesn't break. The problem with that is that if we want to have the same quality of observations every night, the curve of the mirror has to be the same always. So here's where the actuators come into play. We are actively measuring the curve of the mirror and correcting it, so it's always the same, and hence the name active optics. And the other technology that makes this observatory one of the most advanced in the world is the adaptive optics technology. And this is to correct because to the problems with the atmosphere. So I guess everybody has seen the star twinkle. Do you know why they twinkle? Well, this is because the light, as it goes through the Earth atmosphere, is going to go through different layers that have different density, different temperature, different velocity, etc., etc. And this is going to cause the light to deviate a little bit. So instead of going in a straight line, it's sort of going like zigzag through the atmosphere. And we see it as if we start with twinkling. So the solution was to use the adaptive optics. So what is this? When we are doing an observation, a scientific observation, we also observe a known star, a star that we know how it should look in the images, so we can apply the necessary corrections. If we don't have a near star close to our object, we can use lasers. So we shoot lasers up to a layer of sodium that is very high in the atmosphere. These sodium atoms are going to get excited and then going to start emitting light. Now, we're essentially creating a fake star. And we know how this fake star should look in our images, so we can apply the necessary corrections. So those two technologies is what make this observatory one of the most advanced in the world. Now, I think we have some time to maybe answer some questions. Do we have any, Felipe?
I reading all greetings for Amsterdam, Denmark. Go is astronomy. Say thank you, Joseph. And Snowy say I want to visit the observatory someday with my wife and kids.
Well, that
Yes,
is
you
a
can
good thing.
visit. You can visit this. You can visit Paranal or Las Sillas observatories every day in the years. Every Saturday and Sunday, you can visit. You can reserve and visit the ESO observatories. So I invite you to see the page ESO.org to to see the part of visit of every every observatory. In this case, ESO only have a Paranal Observatory and sea observatory, so you can see us in the page, and I hope soon to visit and stay here in the right Melipal, stay in the Melipal telescope. I don't have any question, but I remember the views. Leave your comments, leave your question. Everybody, you know about the telescope, the Hector show. You can ask everything you see. The little the mirror, the cameras, the functionality, everybody you want about the astronomy, star, galaxy, or leave your greetings where you live in the comments. So let's continue meanwhile.
Okay, so one of the questions that people usually make when in the
Mhm.
in-person tours is, do you have to clean the mirrors?
Oh.
And the answer is yes, we have to. And there are two ways to clean the mirror. So for one method, we use this lift over here, and an engineer or a technician will get on that. We will tilt the telescope, and we will spray the mirror with a carbon dioxide foam. And this foam will fall because of gravity, and it will drag any dust particles that are on the top of the mirror. This is done every other week. It's a very simple procedure. There is a more complicated one that is the recoating process. And for that, we remove this entire white cell that supports the mirror. To do that, we use this yellow crane that is over here. We take the mirror to the base cam, so over here, and there in a special building, we use some acid to remove the aluminum layer, and then in a vacuum chamber, we put a new aluminum layer. The entire process takes about a week. During this week, there is no mirror in the telescope, so it cannot be used. And this is done every 18 months, and it's done in sequence. So if it's done today for UT1, 18 months later, it will be the turn of UT2, and then UT3, and so on. Now, at night, there cannot be nobody inside the telescope because all the lights have to be turned off to prevent any possible source of contamination. So the astronomers are going to be in the control room, and this is our next destination. So we're heading to the control room. We can see it here from the side. This building, in addition of having the offices to control the telescope, you also have offices for the engineers, technicians, and so forth and so forth, and also for logistics and whatnot. So we're going to go inside the control room, and as you can see here, there is a sign over here that says UT4, and that is because this area over here is solely to control the UT4 telescope. Over here on the other side, we have for UT3 or Melipal, where we just went before. And if we keep advancing over here, we have for UT1 and also for UT2. And over here we can see a nice picture of the lasers shooting from UT4. Only UT4 has lasers. Now, this entire place is just to control a single telescope. So you may be wondering, how many people work here at night? I mean, there are a lot of screens, a lot of chairs, a lot of keyboards. Well, the answer is that during a normal observation night, there are going to be only two people here. There's going to be an astronomer and a telescope and instrument operator. So these telescopes, they are very advanced and they are also very expensive. So they don't trust astronomers to handle them. There is a specific job that is solely to control and handle the telescope and its instruments. That is the job of the telescope operator. Now, you can think of this as a pilot and a co-pilot in a plane or in a rally car. The pilot, he controls the machine. He's the telescope operator. They are handling everything. The co-pilot, the astronomer, he handles the route. He oversees the science. So he's supervising the scientific aspect of the observations. Now, if only two people work here at night, why do we need so many screens? Well, you have to remember, each telescope has three different instruments. So we might want to have a dedicated computer for each one of them. We also need a dedicated computer just to get information about the weather. If the weather conditions are not ideal, we might need to close. If it gets cloudy, for instance, or if it gets too windy. if the wind speed is too high and a small pebble is lifted up by the wind and then hits the mirror, that would be very bad. There are no replacements for the mirrors, and they were very expensive. So we need to have all these screens because we're controlling the telescope. We also are controlling 3 different instruments, and we also need to receive weather information, among other things. Now, what do you need to do to observe here, and who can observe here? Well, astronomers from every country in the world can observe here, but they need to apply. There are 2 times a year where astronomers can send their observation proposals, and a committee will decide to who they give time and to who they don't. Now, this decision is based only on the scientific merit of each proposal, and these proposals they need to be very, very detailed. They need to include not only what objects do you wish to observe and for how much time, and with which instruments. You also need to mention, has this object been observed before, and with which instruments? How far do you need to be from the moon for the observation to be useful scientifically? Uh, what are your intended scientific goals, etc., etc. And this is very competitive. On average, we get more than 7 times proposals than actual time we have to assign. And for some instruments, it's even more competitive. For an instrument called Muse in UT4, last time it was at about 20 times more proposals than actual time we have to assign. So this is very, very competitive. Okay, so once you send your proposal, if you get lucky and you send a very good proposal and it gets accepted, then there are a couple of choices. There is the visitor mode and the service mode. In the visitor mode, you travel, you sit here on the chair, you supervise the scientific observations. Not all proposals can get to use the visitor mode. It depends on how much time you were assigned to observe, and among other things. And the drawback of the visitor mode is also that if the days that you happen to come to Chile just happen to be the only days in the year that you cannot observe because the weather conditions are bad, well, there's really no space to reschedule the observations. In the service mode, you do not travel here. You send the proposal and the required to enter the proposal to an astronomer of the observatory staff, and they supervise the scientific observations for you. In this case, since the astronomer staff there here the whole year, there is a bit more leeway when it comes to potentially reschedule something, but it's not guaranteed. Now, at about 70% of the time are on the service mode and only 30% in the visitor mode. Okay, so once everything is done and you have the observations, they are private for the PI, the primary investigator that sent the proposal, for about 1 year. They have that time to advance on their scientific research. After that, everything is made available free for everyone. Any astronomer can create an account in the ESO archive website and download the data. Now, usually people don't just do that. They send an email to the astronomer that sent the proposal. They tell them the science that they want to do with those data. And since astronomy is a very collaborative science, people usually agree without any problems. In some cases, they may even ask to be part of the scientific research if it's of their interest. Okay, so this gives us an idea of the process that astronomers has to go when they are trying to observe. But what are the scientific results that we have from these observations? Okay, so to show this, we have a small video with the top 10 discoveries made not only with Paranal Observatory telescopes, but with telescopes of all the ESO's observatories. So, Felipe?
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history. Elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Well, that was the top 10 discovery made with ESO's observatory, but we have a bit of a bonus track. A team of astronomers captured the first image of a supermassive black hole. Please take a look. The Event Horizon Telescope (EST), an array of 8 ground-based telescopes distributed throughout the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole and its shadow. The image reveals the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light years from Earth and has a mass of 6.5 billion times that of the Sun. And there you have the image on the screen. Okay, so those were the top discoveries made with ESO's observatories and with this help of the scientific staff behind them. Okay, so
Uh,
yeah.
we have a few questions.
Mhm.
Um,
Okay.
First question, Hector. Say, how many people are working there in daily base? In daily base,
I don't know the exact number, but it should be at about somewhere between 100 and 200 people. Let's say maybe at about 130. Most of them are not astronomers, but they are engineers or people working in logistic or in IT, things like that. The astronomers are actually in the minority of the employees of the observatory.
and the other question is about those adaptive optic lasers. How do you avoid hitting planes and blinding pilots with them, or there are no fly zone around observatory?
That is correct. There is a no-fly zone around the observatory, and this not only helps to prevent any plane accident, but it also helps us to prevent from any planes to cross the field of view when we're taking an image. So yeah, there is an
That
exclusion
is,
zone.
and that is.
Okay, okay. So as Felipe mentioned you can come here in person. If you ever have the opportunity to travel to Chile, a stop at either La Silla Observatory or Paranal Observatory is a must. And when you come here, you can come every Saturday for Paranal Observatories at there is a visit at 10 a.m. and another one at 2 p.m. These are completely free, but you need to sign up in a website first. Now, one thing that you cannot see in the in-person visits is the night sky from the main platform of the observatory. At night, people are working here, so you are not allowed to be here. But we can see this through the power of this virtual tour. So here we can see the night sky just a little bit after the sunset. We can still see a little bit of light coming from the sun now. So let's start by showing a few things in the sky here. We will start for one of the most easily recognizable constellations, the Orion's constellation that is visible both from the northern hemisphere and from the southern hemisphere. So we have Orion the Hunter. Here we have Betelgeuse the red giant that is supposed to explode as a supernova in the next 100, maybe 200 years. Nobody knows when. And from time to time, it changes its brightness, and that gives us people a lot of interest in whether it's going to explode or not. Over here we have Orion's Belt, or as is known in South America and particularly in Chile, Las Tres Marias, the Three Marys. And over here we have what would be Orion's Sword, and here we have Orion's Nebula, a star forming place. So Orion, in the Greek mythology, he was a hunter, a very good hunter. And in the version of the story that I know, he committed the error of hunting or trying to hunt one of the deers that was sacred to Artemis, the goddess of hunters. So to punish him, she put him in the sky alongside every animal that he has hunted to fight for all eternity. And that was Orion is very close to the Scorpion and to the Bull, Taurus, to Leo, and so forth. Very next to Orion's, we have here Sirius. This is the brightest star in the night sky, and this part of the Canis Majoris, the hunting dog that was together with Orion and the other dog, the Canis Minoris. So over here we have Taurus. This is the horns of the bull, and this is the brightest star of Taurus, Aldebaran. And here, more close to the horizon, we have the Pleiades, a open star cluster. That is a very beautiful object. Now, some of these things you can also see from the northern hemisphere, but let's take a look at things that can only be seen from the southern hemisphere. So over here we have, well, the spiral arm of the Milky Way. That is very impressive. But we also have these two things over here. These are the Magellanic Clouds, satellite galaxies of the Milky Way. So we have the big Magellanic Cloud and the small one. And in the southern hemisphere, you don't have a bright polar star like in the northern. So we can use the Magellanic Clouds to try to find the southern direction. So what we need to do is take these two and build a triangle. So we build it over here to the direction of the Milky Way, and in the missing vertex of the triangle, that is the southern celestial pole, and underneath below, the south cardinal direction. That's one way of finding your way in the southern sky. Another one, we can use the Southern Cross that we have over here. The Southern Cross, by the way, is the smallest of all the constellations. So we take the big stick of the cross, we extended one, two, three, three and a half, some people say 4 times. And we end up at the same point in the sky. So that is the Southern Celestial Pole. And over here we can also see some other recognizable stars. We have Alpha and Beta Centauri. So Alpha Centauri is the closest star to our Sun. Technically, it's a triple system with Proxima Centauri being the closest one. And to finish this beautiful night look at the southern sky, I'm going to tell you a little bit about the cosmovision that the natives of this place had. For them, for the natives of the Andes, the Milky Way was a river, and different animals they will come to this river to drink water. So for instance, over here we have a llama. So here's the neck of the llama, the mouth, here we have one eye, the ears, and so forth. And depending on the time of the year, we can also see part of the body of the llama. But in addition to the llama, there's also a bird, and a snake, and so forth. And I hope you have enjoyed this beautiful night sky. And let's go back to the day. So we are going to head now to our last destination today, the base camp. So here we are at 2600 meters above sea level at the summit of Paranal Mountain. We're going to go down to 2400 meters above sea level to the base camp. And here we have the base camp. And this is a mini city in itself. We have everything we need to work here. We have workshops when we build parts for the telescopes or the instruments, or when we repair things that need to be repaired. We also have mini hospital, places for people to sleep. We used to have, we still have technically, a power plant. When the observatory was first built, it was not connected to the Chilean grid, so it has its own power plant. Later, it was connected to the central electricity grid from Chile, and the power plant was left as a backup. And the latest development of this is that the observatory has transitioned to renewable power. So we're going green. Now, we also have over here a gym, and we're going to go to the Residencia. So the Residencia is the home of the astronomers while they're working here. And it almost looks like we're going underground, but the building is actually constructed on the side of the mountain, and this building won some architectural awards for it. And before we go inside, let's take a look at the desert landscape that we have here, and keep it in your mind how it looks here, very dry and arid, and compare it with what we're going to see inside. So here we have a lot of green, a lot of plants, and we also have a swimming pool. This swimming pool is not just for people to do exercise and swim, which they can do. It's also to increase the humidity inside of this building. The Atacama Desert is the driest desert in the world, and that is not good for your skin and other things. So having this pool inside allows to have higher humidity, and this is also why we have this tropical garden here. Now, this thing at the center is a curtain, and unlike the curtains that we usually have in our homes that we extended during the day to prevent the light from the sun to come inside our homes, what we do here is we extend this curtain at night So the idea is that we can turn the lights inside this building and prevent that light from going outside because it will contaminate the scientific observations. Now, this building had 108 rooms. They are located to this side. Over here we have the reception. There are some offices over here. We have a cafeteria where people can eat breakfast, lunch, and dinner. There is a music room, a game room, a library. You have to remember the people work here in shifts, so they can be 7 days here and then 7 days at home. So they need to have things here to have a more or less normal life. They cannot be just working and resting. They also need some leisure time. And so, as a trivia fact, this building was featured in a James Bond movie in Quantum of Solace with Daniel Craig. And in that movie was the villain's lair. And with that, we are getting to the end of our tour. Do we have any more questions before we finish, Felipe?
We have a one question. Gary say hello for Seattle. Do satellites impact your operations? The
Okay,
satellites.
so this is a good question. And for normal satellites, it's usually not that much of a problem. There are a few of them that are extra brilliant in the night sky, and but we know what more or less the path that they must follow, and we know how to avoid them. The big problem is going to come in the very near future with the constellations of satellites like the ones that Starlink and the other ones to provide internet. Because these are not just individual satellites, there are hundreds of satellites that are going to be passing. And if you look, you can look in Google for images of these constellation satellites, how they affect astronomical observations, and you can see just pictures of a galaxy with a white line or several white lines through the middle because satellites were going through when the image was being taken, and astronomers are actually very worried about this. There are some improvements, like I believe it was Starlink that they did an experiment painting a satellite with a darker color so it would reflect less light, and that helps things a bit. Other thing that helps a bit is putting in higher orbits, but this is a problem that has not been completely solved, and it's going to be worse for the observations in the future.
And this is the old question. And thank you for leaves your question and your greetings. Thanks for your hour. Say I have been there. It's awesome. I hope you visit the observatory Paranal. I hope you visit the East observatories in general. Remember, any Saturday or in La Silla every Sunday, you can visit the ESO observatories in Chile. One is in the Antofagasta region, and the other is in the Coquimbo region. Church, look at the page, the ESO.org, to see how reserved the visit in observatories.
Yeah, and these visits they are completely free. The only thing is that you need to get to the observatory by your own means. There is no shuttle to bring you to the observatory. I also like to mention that you can always go to the ESO website, and where you have hundreds of pictures and videos that you can download and use for wherever you want. And
That's
you can also
right.
find this 360 tour that you can go through at your own pace and see things that we didn't have time to show here. So, with that said, I think it's time to say goodbye. Uh, if you know somebody that is interested in this type of content, please let them know that we have these spiritual tours every Saturday. We are alternating between the Silla Observatory and Paranal Observatory, and also between Spanish and English. So if you know somebody that might be interested, please let them know. And with that, I think it's time to say goodbye. It was my pleasure to be your guide today, and I hope you have a very pleasant day.
So I see you in the next week. The next week I think is La Silla Observatory. 1 week is in Spanish, 1 week is in English. Today is in English. and the next week probably is in Spanish. So I see you soon, and goodbye, everyone.
Goodbye.